And welcome back to this repair video of my INSTEK programmable power supply. I got a shed load of caps that I've put on it and one extra surprise component that I didn't expect I need, and it took a long time to source. So let's get back into the video. Well, let's just get the board back out of the case so we can start the work on it. Well, I did video it, but I've decided that I'm just not going to bother putting it together as a video because it's just me soldering that capacitor, that capacitor, that capacitor, that capacitor, that one, those three there, those two there again, that one, that one, that one, that one down there, that one down there, that one down there, but not these two. And I'll show you a clip of when it was all assembled. It still didn't work. All plugs are in. That's back on. Oh, power line out. Moment of truth. Will it go bang? You're here to be the witness. Button press. And it won't start. After all that. Ah, dear. That's a bummer. More fault finding. Just a quick insert here of how I reverse engineered the board. I had a photograph of the top of the board. I took a photograph of the bottom of the board, and then I flipped the bottom picture over, and so that when you looked down, the components were in the same orientation as the tracks underneath, and that helped. Same way Big Clive does it. So that's how I reversed engineered it so I could get the thing to work. Right, as you can see, this is the reconstruction of the part that went wrong, and it was one of these capacitors, either that one, those ones, or those ones, because effectively they're in parallel, but there's a filter in between. So you see here, there we have our stubborn network. We have the main coil coming in, switched by the drain down to the negative rail, or the neutral line. And there is this feed, there is a supply coming back, which is controlled via the feedback loop through the optocoupler. And this goes into the control. And this sort of, well, obviously, it sets the power so that when this rail is at the correct voltage, then it starts shutting down the switcher So it's standard sort of switch mode feedback loop. There are some noise spike handling filter across each of the diodes, and then you can see there's 2 inductors to filter it. The I call it VCC and VSS. They go off to other boards because they power other parts. They also go down here and go out through the main connector, and that goes off to the logic board. And as you can see, the kind of plus or minus 15 is here. I've got 12 there, but it measures 15 now. It's working. Then you can see that there's this chip here, the reset chip, and that's powered from the 5 volts. But the input is sensed from the 15 volts. When the voltage here goes above the threshold, I think the reset goes high. So you can look at the data sheets for all these parts. But what was happening was one of these was drawing too much current. I think it was probably the positive rail, because if that goes into drawing too much current and the rail drops, the feedback drops out. If it was the negative rail, it might not be so fast acting. But it used to just sit there and go clunk, 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 as this thing was constantly resetting and trying again. I think some of the clunks must have been 1 clunk too many, because after I'd recapped all the caps, turned it back on, it did a few more clunks, and then it died completely. And I did end up changing that chip, and I replaced the optocoupler just to be sure, as I wasn't sure what happened. But I was putting voltages on here and getting no current whatsoever flowing down here. And to be on the safe side, this chip will run at 36 volts. So I put 36 volts across here, and dead as door now, no current whatsoever. And when I replaced it with the new chip, again I put 36 volts across here, and it started to work. It couldn't get the full output because of the transformer. It wasn't designed to work on 36 volts. It was designed to work on like 300 plus. But at least it fired up and it tried to work. So I knew the chip was good. And then I reassembled it all back in the box. Right, here's the 2 differences. This is the original one, which was a top 201 YA. I think it was a YN. But it was a 20 to 45 watt at 240 volts capability. And this is the equivalent, the top 221 to 227. And if we look at a 223, it's a 50 watt. So that's the one I picked because it's the closest to the 201. And if you look, they've just drawn the diagram with a different style. This is the bit of interest where it says replacing top switch with top switch 2, and the 221, or this one is the top switch 2. It basically goes on about checking the transformer design. Well, I can't do that because I have no information on it at all. And then it goes on about clamp voltages and thermal bits, and you might need to reapprove your circuit if you stick it in there. But the only thing is, it does say that it doesn't have the external latching shutdown function, but I don't think that's used. So I plugged it in and it works, and hopefully it will continue working. Even though, unfortunately, if I go back up to the top of this one, you'll find it says this product is not recommended for new designs. But they had loads in all the big places, Farnell, CPC, DigiKey had big stocks of them. So I think they're going to be around for a little while longer. I'm going to bring in the new chip. There's the new one. Let's see if I can find the old one. Here's the old one. There is a slight difference. I'm not sure if I hold it up if I hold it up, it will focus on it. This is a top 223. This one is a top 201. These are obsolete, can't find them anywhere. This is the modern equivalent by the same manufacturer, which they say might work. They ask you to look at the transformer characteristics, but I can't do that, so not much I can do. So one thing I can do is I need to bend one leg, so it's not too far apart, and you can't remove the heatsink. That's where the heatsink goes on. I thought they'd soldered it on and it was a pip, but it's not. It's an Allen screw, and they've soldered the Allen screw to the board and it's screwed into the heatsink, so I can't remove it, which is a right pain, which means everything's got to be done with a heatsink on. Oh, that went in quick. Which also means the screw they supply is very hard to put on because you can't get a screwdriver to it. So I'm having an idea that I might try. Need an M3 washer. Back in a sec. One M3 washer, and the idea here is it's a hex standoff. Now if I could put that in, and get it in the hole, be able to lift it up. Oh, that worked. And of course the idea is now I can use pliers. I was looking for an M3 spanner. That's a Having done that, should I have put some heatsink compound on it? I can't remember if the old one had. Probably not. That's nice and tight. We solder it on and hope it works. Cut the legs off and just refresh the solder because of the vibration. Right, hopefully that might work. We'll find out when we put power on. Just as a little helping hand, I'm going to put some hot melt glue between these caps. Its purpose is just to lock the three caps together as one, to give them a little bit of support. Nothing more. I think that'll do. It's because they're the wrong size caps, and I had to put flying leads on them. For some reason I couldn't find the caps of the same voltage, or caps of the same size. Getting stock was quite difficult. I had to go to some higher voltages, which is better. They're more reliable at higher voltage. Less stress on them, but it meant they're a bigger cam, so it didn't quite fit on the board. But it would do. So, not got much else to do now. We can go back and say that of this board, I've recapped every cap down here, and the issues I've had so far is one of the caps, either one of these or one of them, went low impedance and stressed the switch mode IC that is here. Now that is screwed and soldered to the board, right pain, so you can't get that off. So you have to work on this confined area, hence there is now a hex standoff instead of a screw, because it's easier to tighten up with a spanner. Can't get a screwdriver in there because of the transformer. And that's about it. And I had to reverse engineer the whole of this because there are no circuit diagrams I can find. But I've now got a circuit diagram that's, you know, it may have a few inconsistencies, it may have a few problems that I've not noticed, but it's got the general layout, so you get an understanding of what it's doing. This switch mode power supply generates plus or minus 15. It generates 5 volts from the plus 15 rail. And on this socket going to the board, you get plus or minus 15, plus 5 volts, 0 volts. And there's a little chip down here, which is a reset. And that resets when the 15 volts gets above a certain value. This transformer has multiple windings. It has the plus or minus 15 volt windings for its own power supply. It has a feedback winding that it uses to control the regulation. It has a optocoupler feedback which is controlled by this IC, which is a constant current shunt, I think. So that controls voltage the feedback levels. It also provides a winding that comes down here through that diode there to the pulse width modulation switcher there, which controls the bigger transformer. And this basically, the data for the signals from here go through here, which is a pulse transformer sort of thing, to drive the 2 transistors. They drive this transformer, and the winding from here is rectified by the diode that's bolted to this heatsink. And then it comes through this filtering. And over here is all the over voltage, over current detection circuit, I think, as part of what's on the digital control board here. And then there are 2 wires that come back from the controller board via, you can't see it, there's an optocoupler down here with a capacitor stuck across the top of it. That feeds back to the switch mode or pulse width modulated switch mode controller here. And I think that's how the main logic, which is on this board, controls the output voltage. And then the output voltage comes through over here, as I say, and it ends up going through a FET on here. There's a large FET here and a relay, which is controlled by the front panel. So hopefully now it's time to put the lid back on. We'll power it up and see how it goes. Bring that out. Slide that in. Screws line up nicely, so let's put the screws in. And with luck, this will be the final video on this unit. So hopefully it should give a good few more years of service. And I'll tell you something about the switch mode chip I had to replace, because it took me a while to find out a replacement for it, which was really a stupid time to get a replacement. You would have thought the manufacturer would have said, this chip is obsolete, but we make a pin for pin compatible device, which will probably work, but you may have to check it. And it's available by the thousands. You know, I had to change the part number slightly, but I don't know why the company didn't have a link to it. I would have found it straight away. Instead, I had to try and look for a supply of the obsolete chip, which I couldn't find. And then eventually I came across someone saying, oh, there's this one. I looked at it and it worked fine. All right, so how are we going to do this? I bring the little camera around. Now it's turned off. Put the mains in. Bring the little microscope camera down. Let's pop that on so you can see that. The right way around. Come on, focus. There we go. Right, mains is in. Fingers crossed. Output is off. Let's bring a meter in. Turn the output on. Set to 10 volts, as you can see. Let's wind it up to its limit of 12 at the moment. So there we are, 12 volts. This V limit 40 volts. $39.9, which is good enough for me. That's on coarse voltage, and of course you can put it on fine. Normally I have the V limit set. It's not, this camera is not doing very well at this, is it? It's too much of a reflection. So set to 34, and as you see, I'm only changing the V limit and the output is following suit. I normally have it set, if I'm working on things around my boards and I'm running 5 volts, I normally have it set to like 5 or 6 volts. You can enter that to lock it. There is an I limit, you can set that. So if I'm playing with LEDs, you can wind it right down to like 10 milliamps, and then I don't have to worry about a resistor. I can just stick an LED across it and it will only pull, no matter what voltage it's got on here, it only pulls whatever current is on here. And there's a power limit. You can set a power limit as well. So one of the reasons I want to get it back up and working. And now it's working, I'm going to have a look at the fact that if you look at the label, it's a programmable power supply. It has RS232 input on the back. And so now it's working, I'm going to look at getting a dual or quad USB to RS232 system going so that I can talk to the power supply, my Hewlett-Packard 34401A meter, and use it as a sort of like lab controlled equipment. Well, if you like this video and you want to see more, hit the subscribe button. Don't be a stranger, it costs nothing, it's free to do. Hit that bell. It's also good to do. And hit the like button. Let YouTube know that you like it. And of course, comment down below. Comment away. I love comments. Catch you on the next one.